Okay, so we'll go ahead and get started. So Zoom, I hope, is now fixed. But if you don't see a whole bunch of meetings on the Zoom panel in Canvas, can somebody just like let me know that they're not there, and then I'll see why they keep getting removed. So that's the first big thing. Second thing is a reminder that we will not have in-person class next Monday or next Wednesday. Instead, there will be videos and questions related to this content that we're doing today and the content in the videos for both Monday and Wednesday. And I'll actually put them up simultaneously, so you can choose to sort of like do all your software engineering at the beginning of the week, and then, I don't know, take a 2-day nap or something like that. So that's what we'll do at the beginning of next week. At the end of next week, we'll reconvene in class sort of synchronously, and then we'll go through a review section and then the new stuff for next Friday. So are there any questions, comments, concerns about any of that? It looks like most people have access to Top Hat now. Okay, cool. So what we're going to talk about today, and if we go back actually to this dude, the entire point of, there we go. The entire point of today's lecture is to introduce the idea of waterfall as the way that software engineering happened for decades and decades and decades prior to the rise of so-called agile, right? And so at the time, we didn't necessarily really call it agile, but today what we're doing is contextualizing all of that effort with sort of the old way of doing things and kind of identifying some of the bad parts or the downfalls of that old way. So there are really two categories of downfalls we want to talk about. The first is for individual engineers, right? So you as a software engineer, if you are put into a waterfall project, can expect to have some amount of pain associated with using waterfall, and we'll talk about what that could be. But also organizational issues that face your software company. So we don't necessarily talk a lot about the business or the organization of software engineering in other classes. This class sort of focuses on it. You can think just from like a capitalist perspective, it's really good for your software company to do well. As a software engineer, if your software company doesn't do well, you end up trying to find another job. So it impacts everyone kind of negatively if you don't do things appropriately. So close this and go back. Okay, so we've talked a little bit about this before, but now that we've kind of talked about software engineering in the context of mechanical engineering, and civil engineering, and chemical engineering, essentially what software engineering is designing and implementing some computer component that isn't hardware. And so again, it's really about the corporeal form of the output, right? So if you are a computer engineer, you're very likely building circuitry, you're very likely building peripheral devices or something like that, actual disks or whatever. But as a software engineer, you may have to interact with those things, but even the firmware that you write to interact with those things is non-corporeal, it's not tangible. So there are a lot of things in life that kind of exist on a continuum, right? And so software engineers have started writing firmware that people might necessarily consider hardware, right? So if you're doing things like robotics, certainly there are software engineers that have jobs in robotics. If you are dealing with Arduinos and whatever's, there's a little bit of software engineering and computer engineering crossover. But in this class, what we really focus on is the purely kind of software engineering components of this. So the textbook would have you believe that the most important parts of software engineering are that software engineering provides you a structured, metered way to develop something for a specific purpose. And so this structure and metered bit is about 70% of the class. And what this actually means is that if you were to go and build Microsoft Word, you would have a set of steps that you could then use to build Microsoft Excel and PowerPoint and so on and so forth and so on. And you don't necessarily have to reinvent the wheel in terms of process and procedure, the same way that you don't necessarily have to reinvent the wheel for creating a window for each of those applications or whatever. And back to the last class, it's almost always for a purpose, right? You're not just building a piece of software to see if you could do it. So this is not necessarily hobbyist software engineering. This is software engineering at scale. So all of this is kind of motivated by the stuff that we've been talking about over the last 2 lectures. The predominant idea being that life on Earth in general is extremely complicated. And so if you think about what you are thinking about right now, you're not necessarily just focused on software engineering. You're thinking about the much harder class that you're in or whatever. You're thinking about the fact that you woke up late and didn't get breakfast. You're thinking about what you're going to do in 15 minutes, in 35 minutes, in an hour, in 3 hours, or next week. And tomorrow, if you were to pull your brain, what are you thinking about right now? It would be a trillion more things, right? And there would be very little overlap. You're almost always thinking about classwork that's due or whatever, but there's always going to be some new sort of niche thing that you're considering at any moment. So software in general has been used to rein in a lot of that kind of like free form, unstructured sort of complexity in everybody's life. You have to-do lists, you have word processors, you have things like Canvas, you have your planner on your phone, you have calendars, you have whatever. And in addition to those things, you have software that interacts with the sort of physical world. And so you have a timer on your coffee pot that tells you that it's time to wake up. You have your car that is capable of talking to a satellite and giving you music and whatever. And so again, you can't really get rid of software. And so what we really need to do is make sure that the software that we are creating actually works and doesn't have any sort of glaring issues with it. And so people talk all the time about America running on Dunkin', but what it actually runs on is software, because without software, there probably wouldn't be a Dunkin' Donuts, because they wouldn't have been able to mass produce donuts that people want to actually eat. And they wouldn't have their app that allows you to ask Dunkin' Donuts to make you a cup of coffee, and it will be waiting for you 90 seconds from then. So even things that you don't necessarily think of being software very often have some percentage of them that is actually software. So this obviously comes with benefits and sort of downsides. So the benefit, again, humans get to live with a lot less complexity. You get a whole bunch of really cool, snazzy stuff that makes you feel like you're in Star Trek: The Next Generation. And extremely critical processes become instantly repeatable. If you think that you used to work at a bridge, and if you saw a ship, you would run across the bridge and hit a button so that the ship didn't hit the bridge. Now we have sensors that could do that for you. And if you forget to go to work on a day, or you sleep late, a ship isn't going to just ram into the bridge because it expected a human to do something. And this kind of automation helps limit failures, and it helps eliminate mindless work. So I think it's something like 70% of bugs are created by a software engineer having to do something like copy and paste code, and they forget to change a little bit of the code after they paste it. That exact same idea translates to effectively every job that you could possibly have. What you don't want is you don't want your heart surgeon doing something that's mindless, because their brain will be on 40 million other things and not making sure that you don't die. And so software plays a critical role in these kinds of processes. So the downside, we talked about this a little bit last time, but because it's complicated, it tends to be huge. And because it's huge, it tends to be really, really hard to actually get right. Oh my gosh, I forgot to record. Oh no, I did. Excellent. See, mindless things, exactly that. So it's really hard to get right. And as a result, of being hard to get right. You have to have fairly large teams that help you actually put all this stuff together. You have to have another team that's different from your development team testing that piece of software. And the issue there is now you have multiple types of people and multiple types of teams inside of your organization, all striving to do ostensibly the same thing, but maybe with different priorities. Okay, and like we talked about last time, software failures are effectively a part of your everyday life at this point. So very frequently you will go to Canvas and you will log in, you will get a gateway error and you will snap your fingers and say, gosh darn it. And then you'll go away and you'll come back 15 minutes later and you'll reload the page, everything's cool. So people started kind of living their life with bugs or with software failures, especially minute ones. You've almost certainly been writing a paper very late at night and had Microsoft Word crash before saving. All of these types of things are sort of detrimental to your life, but they aren't necessarily the scale of detrimental that we talked about last time. And so these failures exist on this huge continuum. It could be something as kind of trivial as the blue screen of death, making it impossible for you to join a lecture or to take a test, all the way up to Boeing 737 falling out of the sky because it doesn't want to listen to the pilot. So because there are so many different types of software and because there are so many different sizes and shapes of software, it's really hard to take one sort of process and put that process on top of all of them. So we talked about the Tacoma arrows last time, but if you think about what would happen if you woke up and on the television, you learned that effectively the Brooklyn Bridge just fell into the East River. People would be really freaking out. There would be sort of mass pandemonium. There would be all of these hearings about what kind of bridge it was and if we need to go and sort of restructure all of the bridges of that same type or all the bridges that were created by that same group of people. And that is not at all the kind of backlash you get when the blue screen of death happens to you, even if that blue screen of death sort of sets off a chain reaction of things that could be quite detrimental. The blue screen of death on your machine, kind of a big deal. The blue screen of death on a machine, managing safety of an international gas line or gas pipeline, obviously much bigger kind of problem. So we talked last time about some specific software disasters. These are some of them. Wow, all right, cool. So these are significantly different ones from last time, just to indicate that those are not an exhaustive list. And even if you add these to the previous ones, not an exhaustive list. This top one, Therac 25, is one of the probably weirdest ones. This was a radiation sort of type of system, almost like an X-ray. And because there was a failure in the controller, it actually started dosing people with an order of magnitude more radiation than it was supposed to. And obviously that's not a great situation. And then obviously the Boeing 737 MAX bug from a couple of years ago was a pretty big deal. Okay, so it's in general pretty rare for one of these sort of like deadly events to sort of happen. And in a lot of ways, regulation does come about because of these. And so because of Boeing 737 MAX, the FAA got much more involved in software engineering and what the product a software engineer was actually creating did. And it's good, right? Like people want fewer fatal disasters, but there are tons of non-fatal disasters that also kind of go under the radar. And so in 2003, I'm trying to think of how old people in this class would be in 2003. 5, 4, 3, yeah, a very small number. But in 2003, there's actually this thing called the Great Blackout. You probably don't remember this if you were 3 or whatever, but the exact same bug that was in Therac 25 actually showed up in a power grid controller in the Northeast. And so the ramifications of this were millions and millions and millions of people being without power across multiple states. There have also been extremely large travel delays caused by issues in flight controller or airline flight controller software that sort of orchestrates when it's safe and when it's not safe to fly. Fortunately, in this case, it always just assumes that it's not safe to fly until it otherwise is told. So it doesn't necessarily cause a fatal issue, but it causes lots and lots of people to be very, very angry. And this last one is sort of fun because it was effectively one of the first AI kind of financial trading systems. Tons and tons of people bought into the system. It ended up losing tens and tens of millions of dollars overnight because it effectively sold at a trough instead of selling at a peak. So their cost function was backward, which is not a great situation at all. So essentially it was buying high and selling low. That's 2 thumbs down from everyone. And so this also became like a sort of a huge congressional kind of issue. So this all leads down to what we want to talk about today, and that is what can we actually do about any of these things? It's sort of fun to talk about everybody else's failures and sort of laugh at them, but if you're going to be a software engineer, you don't necessarily want to be the person who's on this PowerPoint slide, 25 years from now. And so the point of software engineering is really to identify different types of software and figure out how dangerous that piece of software could be in terms of not only safety, but also just in general collateral damage. So production software itself is really, really big. It's complicated. And at the end of the day, it's important. If it's not important to a consumer, it's important to the software company that actually generated it and is attempting to make it important to consumers. And so typically, if you are going to treat that production software like you treated programming assignment number 2 in a randomly selected programming class, you're going to have lots and lots and lots of issues. So you're not going to necessarily be able to do the same ad hoc things that you would otherwise do. So you're not going to be able to take the source code and then identify a bug and then in a matter of 3 or 4 minutes, fix the bug and then test the bug and then rerun the application and everything's fine. So if you were to release a production piece of software, even with a stupid bug, you would have to go through this whole testing process and then notify potentially hundreds of thousands of people that you screwed up and that you fixed your screw up. And that takes a fairly long period of time usually. So software engineering, and the reason why many computer scientists believe that software engineering is sort of a soft kind of thing, is that software engineering is almost equally, if not more, about the process and the pattern and the steps that you take to generate the software than it is about the actual code behind the software itself. So what we're really talking about is we're talking about all of the kind of steps that you can take along the way to ensure that at the end of the day, you don't end up on the software disasters slideshow. So ultimately, what we want to do is generate software that has these 3 kind of properties associated with it. 1, you want it to be stable. What that means is when a person logs in on a Tuesday, the system does exactly the same thing as when they logged in the last Tuesday or the Monday before that. You want it to be scalable, which means that once Canvas picks up its 10,000th user, suddenly Canvas doesn't fall apart. And you want to make sure that you could actually extend it. So there are 2 types of scalability. Scalability in terms of features, scalability in terms of usage, and we want to make sure that we're hitting both of those. And the hardest one, defect-free. So ideally, we would be generating software that does not have any bugs, and the bugs that are there would be very, very minuscule sort of inconveniences and not things that could actually put collateral damage kind of in the forefront. Okay, so there has always been a need for software. And so you've probably heard of the AI boom. You've also probably heard of the .com boom. And before that, there was this massive boom in terms of software engineering as computers became smaller, as computers became more reasonable for companies and for universities, national labs to actually get. So because of this gigantic boom, lots and lots and lots of software projects got started, but nobody actually understood or stopped to think about the best ways of doing things. So effectively, it was a situation where technology became very readily available. A whole bunch of different companies and a whole bunch of different universities wanted to use it at scale. But early software engineers were really just software developers, right? They didn't have any of these processes in mind, and no research had really been done into how to build these systems that were drastically different from programming assignments or from small scripts that people had been doing in years before. So what they effectively did is identified, hey, if we just run into this headlong, sort of Leroy Jenkins style, potentially we're gonna have tons of problems. And what they ended up doing is they adopted this thing called the waterfall model from construction and manufacturing. So essentially equating software engineering with civil engineering or with mechanical engineering, they realized that at least this would give them some sort of steps along the path, and they may not be optimized, but at least it gave them some sort of template to kind of work from. And so with this idea, what you do is you group all of your kind of tasks together into a series of sequential phases. And the problem with this is that the sequential phases have extremely strong dependencies. And that means that when you go to phase 1, you can't just skip phase 2 to go to phase 3 for a minute and come back. You have to finish all of phase 1 and then go to phase 2, finish all of phase 2, and then go to phase 3, so on and so forth. So if we look at what waterfall looks like for construction, it starts with developing blueprints. So if you're going to build a building or if you're going to build a bridge or whatever, you're going to have to go to some sort of municipal government and tell them, hey, I'm going to build a building. In Tallahassee, at least in the city limits, you can't actually change your door, the front door to your house, without getting a building permit. That's what this is. So once you get an idea of what somebody wants the building to look like, how many bathrooms does it have, how many floors does it have, is it supposed to be made out of concrete or wood or brick or whatever, you would develop the blueprints. You would then take the blueprints to the government, and then you would get a permit for each of the permittable kind of items in that blueprint. The next step would be actually going to the site with all of your dump trucks and your back hose and all of that. And you would actually prepare it, right? So you would level out the earth, you would pour the foundation of the building. And at this point, you start getting into unrecoverable issues if you don't do it correctly. So what happens if you pour the foundation and somebody told you that the bathrooms all needed to be in the southwest corner, and then they changed their mind? Oops, they're supposed to be in the northeast corner. You've already run lots and lots of pipe through lots and lots of concrete, and you're going to basically tell the client that they're going to have to live with it effectively. So back to tight dependencies. You have to have the permits before you can pour the foundation. You have to pour the foundation before you can frame the building. So if you don't have a foundation, you have nothing to actually put the frame on. And after you frame the building, if somebody wants to change the entire layout of the building, you're going to have lots and lots and lots of problems. And after that, obviously you do all of the kind of finishing. So you go in, you put the electrical work inside of the walls, you do the drywall, you do the plumbing, and you put the pillows on the couch in the lobby, and then everybody's kind of happy. The contractors get paid for all of their construction work. The bank or the university or whatever gets to move in and use the building. Everybody is kind of happy. As an FSU student, you have seen all of this crap every time you've walked around the union. So you can imagine like the long term nature of some of these things, right? Develop blueprints and acquire permits was a multi-year kind of thing for the union. And obviously plumbing, electrical, drywall, and finishing seems like a thing that will never be done. So these are very long-term projects, but the key here is that you can never start plumbing and then think to yourself, oh crap, we need to change the blueprints, because that is not going to be kind of an allowable thing. Okay, so that brings us to the main sort of crux of why software is much harder than any of these other types of engineering. And that's because software is not corporeal like a building. You can't go to the site and look at the software. You can't touch the software. And so as you're trying to understand what the client actually wants, it's much, much harder for them to even go to Pinterest or whatever and tell you what the software should look like. So it's very, very hard for the client upfront to provide you with a sufficient amount of information for you to build the blueprints. So because of that, it is really, really hard to hold the client accountable for any changes they want to make after, huge air quotes, the foundation is poured. So this happens over and over and over again. And the easiest kind of metaphor for this is the age-old checkbox problem in software engineering. And I'll kind of explain that. So imagine you are sitting in your cubicle and you're working on an application that has a grid, and in each of the rows, it's going to contain a to-do item that a person has to check off their list. The first version of your piece of software didn't have an actual checkbox to have the person check. They had to double click and then choose complete out of a dropdown. The project manager thinks that that sucks and they want you to add a checkbox to the row. There are specific architectures that make that an almost impossible task. So if you think about the ease from the perspective of a project manager of putting a checkbox on a row in a grid, it's very, very minimal. That is something like somebody telling you, hey, you put the toilet in the corner. I actually wanted the toilet to be 3 feet from the corner. In order to do that, you're going to have to take a pickaxe and then bust up all of the tile. And then you're going to have to get a concrete saw and cut half of the concrete out between where the thing is supposed to be and where it is now. And then call the plumber and get the plumber to come back and run more pipe and then physically move the inlet to where it's supposed to be. And so it might seem really easy to move something 3 feet over, but just logistically and pragmatically, it's not. And in software engineering, it's much harder to understand when the ask that you're giving to a software developer is an impossible task versus is something that's really, really easy. So this all gets wrapped up into the fact that stakeholders, until they have something that they can actually execute and they can go in and they can look at dialog boxes and they can look at grids and they can look at the login screen, it's very hard for them to think about what it's going to look like. People have seen buildings for hundreds of years. And in a lot of cases, people can just kind of suss it out. Software is a much more open sky, blue sky kind of thing. And it is almost impossible, especially for an older stakeholder, to, in their brain, come up with all of the individual requirements in order to give you something that's actually going to work from day one. So what the waterfall methodology looks like for software is very kind of similar to construction. And so this is the way that software was done probably all the way through the late 80s. And that is to gather as many client requirements up front as physically possible, then use those client requirements to develop a specification and the design based on that specification, and then give that to the client and then have the client sign off on that. And then once you have sign off, you're going to go out, you're going to get all of the different sort of niche engineers, right? The UI guys, the front end and the back end developers, some full stack developers that kind of understand the entire pipe. And you're going to build the thing out. And then you're going to let the client into the system. You're going to tell them to kick it around for a while. You're going to triage all the issues that they come up with. And then you're going to do what's called a formal handoff. And that is you give the CD-ROM or the whatever to the stakeholder, and they sign a document that says, I'm never going to shout at you about this piece of software again. And then you go your separate ways and everybody's kind of happy. This handoff thing goes back to what we were talking about in the COBOL systems for the state, right? So if the state still had an agreement with the software engineering company that built that COBOL system, they could have knocked on the software engineer's door and said, hey, everything's broken and we need to send out 1 million checks, and somebody would have come and helped them. They couldn't do that because of a very rigid sort of handoff practice that happened that afterward absolves the software engineering company from actually having to remediate any major issues. Okay, so it turns out that in life, as in software engineering, change is really the only thing that stays the same. Things will always change. It doesn't matter if it's a requirement or if it's technology or if it's the people who are actually doing sign off at the firm that you're working for. Change is constantly happening. And so what happens when we get out to build the system? And then somebody brings up the fact that you assumed that we were using Windows PCs or Mac PCs or Mac OS machines. And actually what we're doing is we're using an ENIAC machine that we got from a garage sale. And now all of the code that you've been working on in terms of C++ or in terms of Java is clearly not going to work because this is a vacuum tube machine. So you're going to have to go out and like find some people who understand how to build mechanical programs, and Godspeed. So what's going to end up happening is you're going to get this extremely passive aggressive email, and passive aggressive email is going to indicate to you that you have to redo what could be years of work, and little smiley face emojis at the end indicate that they expect it to be done, post haste, right? Like they don't want to necessarily lose a bunch of time. So at this point, software engineers typically sort of get up and they go to their car and they scream a lot, and then they get on dice.com, they start looking for another job, or they pick up their machine and wish that they could throw it out of a window. And so these kinds of very disruptive, very large scale kind of changes happened all over the place in classical software engineering, to the point that the stats are that more software projects failed than actually succeeded by a lot. And so even in 2015 or 2016, working at a software company in Tallahassee is not unheard of for software projects to go over time budgets by years, over actual monetary budgets by hundreds of thousands, if not millions of dollars, because of this kind of stuff. So what typically would happen, somebody like me at my software company would then have to write this email to the client. And it would say something like, all right, cool. We built this whole system assuming that, you were using machines from, I don't know, this century. And if you aren't, then we have a big problem because we have software engineers that now have to pay their rent, and you have to actually pay us something or they're going to be homeless and they're not going to be really inclined to build your system. So ultimately, this becomes a really hard thing for an organization to do. Most of the time, you're not going to get your $150,000, and you're going to have to lay off software engineers, or software engineers end up taking a pay cut, or the whole company just kind of goes under because it can't actually bear the weight of its payroll waiting on somebody to pay them that may never pay them because of a failed project. And so this is kind of the worst case scenario that we're trying to keep from happening by all of the sort of procedures and processes that we bring up in this class. So this is the game over screen of software engineering, and all of the kind of regimented practices that we're going to talk about through the semester are attempting to keep you from ever seeing this end of game over screen. So this allegory itself, it feels a little bit absurd because you're not going to necessarily have an email from a client that they're actually using machines from like 1951. What is much more likely is that the client is going to want very, very minor changes, but they're going to want 10,000 of them. So if the color of the login screen or the text on the login screen's button changes every other day, that's an extremely minor change, but it requires a software engineer to go into the CSS or to go into the HTML, or God forbid, to go into the WPF and update that value over and over and over and over and over again. All of the time that they spend doing that fragments all the other time they could have been using to actually solve meaningful sort of issues. So this issue in and of itself seems kind of crazy, but it is indicative of a larger problem. And that larger problem is that the stakeholders at the bank, or the stakeholders at the law firm, or the accounting firm, or the university are much more concerned about their business problem than they are about the actual system that is going to fix that business problem. And because of that, they do not necessarily care or know a lot about the technology that you're using to build that system. So this is an example of a client could come to you and say, yeah, great, we want it to be a web app. And you start building a web app. And about 9 months in, they start asking you about mobile apps because, you know, the competing bank across town now has a mobile app. And you have to think to yourself, okay, like maybe we could make this a React Native mobile app. Or we could say, hey, no thanks, we're going to finish the web app first because that's what we've kind of agreed to. And in Waterfall, basically what you would have to do is start all the way over if you wanted to kind of build an application that seems like it's similar, but is on a completely different framework. And there is a whole idea around know it when I see it development. And this is a part and parcel to Waterfall. If you don't start building the application until the 3rd phase, that means that potentially going back to the union, right, it's going to be 2 years before the stakeholder ever actually has anything tangible on paper to indicate to them if their initial design decisions were accurate or good or bad or whatever. And so what could happen is you could get all the way through phase 1, all the way through phase 2, start building the application, and now suddenly the law firm or the bank or whatever is going to identify lots of business problems in your solution to their larger business problem. They're going to identify that they actually need much more rigid security than they initially asked for. They're going to need a much larger number of users than they initially asked for. They're going to need a much larger number of screens. They're going to need administrative screens in the application that they didn't tell you about. And so all of these kind of things can make a 1-year project turn into a 10-year project if you don't kind of put them on rails pretty quickly. So the kind of bad word around all of this is that fundamentally software engineering is a business. And the moment that you accept some of these changes, oh, great, we'll build you a mobile app, no big deal. You're not going to get paid for 100% of those hours because the client is always going to come back to you and say that it's rework. And so clients are never going to want to pay 100% for rework. And once you do this over and over and over and over again, you start to onboard lots and lots of organizational issues. You run into situations like you only get paid maybe 50% upfront for the project, or you only get paid by the hour to work on the project. And now you have a situation where you have engineers that are working day and night trying to make something happen, and you have no collateral or no cash to actually go out and pay them. Very few people are going to want to work for free. So we're going to talk about this situation specifically in the video on Monday. But fundamentally, there are 2 ways that you can look at software engineering being a business. You can do the whole Facebook thing where you don't necessarily charge anybody any money, but you find a way to capitalize on their data or capitalize on something that you took from them that they didn't realize that they had. And from that perspective, software engineering being a business is this effectively unfettered capitalism kind of situation. And this comes from the idea that you don't necessarily have to have a ton of outlaid cash in order to start an application. The 3 of you guys could decide, we're going to go out and build a React app, and you could have one stood up probably by the end of the weekend. And the collateral that you have or the capital that you have in that application is 72 hours and I don't know, like whatever food you ate while you were doing it. It isn't the same as a building, right? Like you're not going to go out and buy millions of dollars of marble to put inside of your React app. So it's easy to start a company. So it's easy to start a startup in tech. It's harder to make it sustainable because you have to find a way to make the development of software mutually beneficial for both your organization and for the company that you're actually producing work product for. So when the bank comes and tells you that they have a mission critical change, right? We have to have this additional security because we're going to start doing business in Europe or whatever. There are going to be changes that you absolutely have to adopt. And there are going to be changes like we want the login button to be green instead of blue, that you need to push back on and tell them that what they're actually doing is spending their money in ways that they don't necessarily want to. And so with waterfall, it's hard to distinguish those two things because effectively after you've laid the foundation, there is very little, if any, wiggle room to adopt a change. What we want to do is move toward a better kind of approach to these things where we can identify which changes we would like to adopt, which changes are going to be a really bad idea to adopt, and then kind of work together from both the client perspective and the software organization's perspective to figure out what to adopt and when. So if you are wasting resources as a software engineer, if you are taking way too long to implement a database, if you are kind of re-engineering the database over and over and over again because you keep finding new fancier ways to do it, eventually somebody has to pay for that. It's either going to be you in terms of losing your job because the company lost the project. It's going to be the company for hiring too few people and giving you too much work. Or it's going to be the client for continuously rethinking their entire design or continuously kind of dragging their feet on making decisions. So when I say software engineering is a business, I mean it in the most tautological sense. There's no value judgment placed on it. It's just that if you work for Google, this is a much smaller problem, right? Like Google has closets where money just kind of falls out of them. If you work for a company that has a software engineering department inside of it, many insurance companies do now. State Farm has many internships in Tallahassee. This becomes an increasingly large problem. If you decide that you're going to go out on your own and build the next great video game, this is going to be extremely problematic for you. Because if you're trying to build a huge video game by yourself, every wasted minute is going to be really, really kind of cumbersome to get past. Okay. So in addition to all of these kind of technical challenges, software engineering also has a whole bunch of issues that are, because software engineering is a business, typically taught in a business context, right? So people who are getting their bachelor's in business administration would definitely be able to sort of navigate a lot of these like resourcing issues or timescale issues or whatever. You guys that are classically trained in C++ and like theory of computation and software engineering are not going to be as adept at doing those things until you do it, right? So the first 5 or 6 or 7 times that you're on a software engineering project that's client facing, things are really weird and you start doing things that you wouldn't have necessarily understood. In programming 2, we're going to be part and parcel to your job. So emailing clients, trying to understand what the hell their emails actually mean, trying to work a client through decision-making, because you as a software engineer provide the technical adeptness, and the client as a banker or as an administrator at a university brings all of the domain knowledge. And effectively what you have to do is mash those two things together in such a way that one doesn't overpower the other. So what our goal is in this class is to find ways or illustrate ways where we can take domain knowledge and technical knowledge, put them in a blender, and at the end, come out with something that is actually functional, that you can take to a software engineering job day one and kind of understand where all the pieces are and what all the steps are, trying to go from the idea of an application to the implementation of an application to the delivery of an application and the support and maintenance and evolution of that application. So what we're going to do in the videos on Monday and videos on Wednesday is we're going to go specifically through some of the downfalls of waterfall, and then introduce the idea of agile as a way of kind of getting around a lot of those downfalls, and reimagining this process, not even thinking about buildings, right? So accepting the fact that software is always going to be different than a bridge. We're going to kind of illustrate how agile has rose to power as the kind of de facto way of putting together large-scale software systems. All right, cool.
Are there still any cases where people use waterfall?
Yes, there absolutely are. So Waterfall has been rebranded. And so now you have agile processes and you have what are called planned processes. And so the planned approach to software engineering is effectively Waterfall by another name. And so the long and short of it is if you have a small project and you have a very tight timeline on that project. So if a person says, I need a bot that's going to send an email every time I hit a big green button and I need it by next Friday, Waterfall is the way to go. And it's the way to go because Agile has so many meetings and it has so much like overhead that you're going to exceed that week just trying to plan for it. In a Waterfall sense, if the project is that simple, the email kind of tells you exactly what they need it to do. You put everything together, you give it to them as an MVP, which we'll talk about later. And then you can always iterate over a project that was started as Waterfall by just kind of accepting the fact that it's not going to be right the first time. Cool. So are there questions, comments, concerns about any of this stuff or about any of the kind of soft intro to software engineering before we start going through kind of the litany of steps and all of that stuff starting on Monday? All right, cool. So I think that is going to be it for today. You get almost 20 minutes of your life back on a Friday. And I will see you guys next Friday. So again, I'll be posting the videos and all of the questions that are associated with those videos starting on Monday. I'll try to post them all at the same time so you can kind of get it through if you'd like. All right, cool. So thanks everybody, and I will see you next week.